My name is Joe Canary. This is Dan Zimmerman.
Hello.
We pitched a strangely titled talk called Formal Methods Need Not Be Black Magic. And they put us in this particular track in part because at our company called Galois, we do an awful lot of security stuff. And much of that touches on the use of formal methods. So part of this talk is to do a bit of cheerleading around getting folks in the audience interested in or understanding about formal methods, and in particular, applied formal methods for secure hardware. I'm going to do something now that I hate when people do it in talks. I'm going to ask you to raise your hands. I'm going to ask, thank you, Greg. I knew someone would do that. Jumped right in there. All right, so this is a talk about formal methods and its application to, say, secure systems development. And that means that we have to focus on hardware and software. How many, and I know there's a lot of hardware engineers in the room. How many folks in the room have used a formal methods tool to reason about hardware systems for more than 1 month? All right, that's like 24 people. That's a new record in my lifetime. I'm very excited to see that. Now, partly what we'll be talking about today is a bit of a history lesson on formal methods through the ages. The reason this is necessary is because modern formal methods, and in particular applied formal methods for secure systems development, are radically different from what you learned in college or what you might have heard about. And then we'll talk about some of the ongoing work in this topic at the intersection of formal methods and secure systems engineering that Dan and I are working at with others at Galois. Dan?
Yeah, so formal methods is essentially applying mathematics to problems in computer science and systems engineering. So computer science came out of 20th century mathematics and logic. Computer and electrical engineering are sort of a combination of computer science and physics. Physics, of course, came out of mathematics. And so formal methods is sort of a natural step along the way here. Now, initially, when the original ideas about using mathematics to tell you things about computer systems was developed, basically it was viewed as this is something that only PhDs in the area are going to be able to do. It's really esoteric, hard to use, takes ridiculous amounts of time. And yet, in the late 80s and early 90s, formal methods started being used a lot in hardware verification because of a number of fairly expensive failures in CPU design and testing that led to companies having to spend lots of money. However, even now, most hardware design firms have like some small group of people that do the formal. And everybody else kind of views that group of people as, well, they're the only ones that can do it. They've spent all this time learning it. They're experts. Maybe they're magicians. And that's kind of the way it's viewed. And the vast majority of people at these companies don't actually use formal tools. So 50s to 90s, esoteric. On the software side of things, though, formal has developed very rapidly. So in the late 90s, we started to be able to use formal methods to deal with things written in mainstream programming languages. But it still took a lot of work, and it still required a lot of expertise. In the 2000s, as computers became faster and faster and had more and more memory, we had the ability to do this for even larger systems. And so that is really distracting. Apparently, we don't do it for display systems. And so formal methods, by taking advantage of all of this processing power and memory, started being integrated into things like IDEs and mainstream compilers and things that basically all software developers ended up using. Static checking of semantics of programs. The Java virtual machine class loader doing verification of loaded classes before it executes them, that sort of thing. Later on, more attention has been paid toward user experience and integrating it into even more mainstream tools. So it is basically impossible now to find an IDE for any mainstream programming language that doesn't have some formal methods-related tool embedded in it somewhere. The usage of these things has basically become pervasive for software engineers, but they don't need to know the math, right? You program in a language, it has a nice type system, it tells you nice information about the kind of things you got wrong. You don't need to know all the logical formulas that went into that. It's almost as though it's been snuck into the software engineering workflow. And we call this Secret Ninja formal methods.
That's where you go do this.
Yeah. So Secret Ninja formal methods is a systems development methodology that we defined about a decade ago and published at a conference actually 10 years ago. And the idea is do your system design and development in a verification-centric way so that it is easier to apply all of these methods and tools to actually achieve the results you want. And so lately, we've been applying these techniques to hardware engineering and hardware verification. And the main idea behind this, which I already sort of alluded to, is the mathematics behind it is completely hidden, right? Nobody has to sit down and manipulate logical equations directly in order to get the benefit of these tools. Instead, what we do is we expose specification artifacts and the reasoning behind it using nice, friendly user interfaces and development metaphors that people are already familiar with. So the methodology has 6 main parts. Specification, that's where you describe either the functional behavior or the non-functional properties you want your system to have. You can then extract formal models from specifications, but also you can extract them from existing implementations and start trying to reason about what systems you have already do. Implementation, you build parts of your system according to your specifications and models. You can execute systems, of course. Validation is when you actually augment the execution of your system with runtime checks that tell you whether it's doing what it's supposed to be doing. And then verification, which is formal checking of models for correct behavior under all possible inputs and environments. And the important thing about this is not a waterfall-like, this is actually an upward waterfall. But this is not a waterfall-like development model where, okay, we did our specification and we got it perfect and it's all done and now we move on to doing something else. It's more of a spiral where you do some specification, you do some modeling, you sort of build some small part of your system, you see how it works, you see how it verifies, maybe you need to update your specification, and you iterate along these lines for a while. And we've taken this methodology and implemented it on the firmware and software side for a bunch of different programming languages over the last 15, 20 years. For Java, there are a whole bunch of different implementations of this. And I'm not going to read all of these because you all can read and you will get the slides later, and we don't have time to talk about them all in detail. But Java, .NET, Eiffel. Anybody use Eiffel? Yeah, Eiffel is cool. And Eiffel is actually where sort of the design by contract idea was initiated. Also, Spark. Spark is a very nice evolution of Ada. C and Rust. Lots of people, I imagine, use C in this room. And various functional languages, things like Haskell and ML and Idris. So I'm going to hand it off to Joe to talk about hardware-related things.
So Dan and I started playing with hardware, learning about hardware development, and in particular working on things like building CAD tools for hardware back in the late 90s. And then we moved out of the hardware world and did formal methods and software for a long, long time. And recently we've gotten back into hardware. And at the moment, once we did that, we started to poke around and see what was out there with regards to tools that called themselves formal methods tools, and tried to better understand what they did and what they were capable of. And we found that contrary to the world of software, there was basically nothing out there that was free, to the closest approximation, that would let us do formal reasoning about hardware. Moreover, the tools that were out there that you could purchase or license for large piles of money would not describe to you the reasoning techniques they used. They were all opaque black boxes. We found that a bit frustrating. So we're like enthusiastic about Clifford's work and use it as part of our stuff at Galois. But we also use Cadence's stuff and Mentor Graphics stuff. And yet we're spending as much time using those tools as we are reverse engineering what they're capable of doing. Under development right now is a new tool suite called the Bespin tool suite under the auspices of the SIF program from DARPA. And that tool suite gives us new reasoning capabilities about systems in the main, but in particular hardware systems in specific. And by virtue of the shape of the SIF program, we are asked or forced to build tooling that spans multiple dimensions. In particular, it's capable of understanding and reasoning about 5 different HDLs. The program focuses on RISC-V chips, which is why we're here and why we've come here for a number of years. It permits you to extract architecture specifications from implementations. It permits you to extract feature models from implementations so that you can reason about the plethora of configurations possible, as we just saw from Jack's talk. It permits you to configure those models into products at a high level, much like Sci-Fi does, but now spanning other kinds of HDLs. And it facilitates the measurement and evaluation of power, performance, area against security goals and against security specifications. The core idea here is that some clients out there, some of you, are willing to pay for increased security by giving up something else, by giving up some area on your chip, by giving up some performance, perhaps by giving up some power. There's a space of configurations that we can explore interactively so as to facilitate evidence-based decision-making around how secure you want your chip to be. Now, the trick here is that security specifications are oftentimes about saying things like, the following thing doesn't go wrong, or the following kind of thing never happens. And the unfortunate situation is those kinds of specifications are not the kinds of specifications in general you can test. We can't use traditional hardware verification, i.e. running programs, I'll just be blunt and call it running programs, to test for such properties, which is why in the main, formal verification is not just a good idea, but it's the only idea to reason about these kinds of properties. So let me dig into this topic a little bit so you see where we're heading. Behind the scenes here, of course, there's an enormous complexity. Somebody has to do the hard business of formalizing the meaning of these, say, programming languages or design languages and the like. And what we hear about a lot in the hardware realm, especially if you use current commercial toolings, is that state space complexity is a killer. You know, you have an adder and you go from 4 bits to 5 and suddenly everything falls over. That's because in the main, the reasoning techniques in existing commercial EDA tools are reflective of formal methods in the 80s, 90s, and early noughts. They are not reflective of work that's been done since then, mainly in the world of software and firmware verification. So it's sort of a red herring. You shouldn't think about modern approaches to formal methods from this point of view. In particular, the thing you really care about is the shape and nature of your system. Is it a sequential system? Is it a system that witnesses a lot of concurrency? Is the concurrency of a structured nature that we can reason about and understand? Is the system designed in a rational way that's compositional so that we can understand that the pieces work independently and stick the pieces together? Now, here's the interesting thing. A lot of people say hardware's hard. I would argue software's worse. Software is a big steaming pile of crap in the general, right? The programming languages we have out there in the main are bad. They're really hard to reason about. There's tons of awful design decisions in those languages, and people abuse them when they write code. I mean, for God's sakes, most of my students for years, when I was a professor, ended up solving problems by cutting and pasting from Stack Overflow. I hope that Stack Overflow doesn't take over the world of hardware design, or we're all doomed. So the key thing to ask yourself here is that, do we design hardware systems in a principled way that might lend themselves to a smarter use of modern formal methods? And what we're finding over and over again is that old school pieces of hardware that we're asked to reason about and dig into are awful in the main. And modern pieces of hardware that we look at, especially stuff that comes out of the RISC-V community that leverages modern HDLs and modern tools like the world of BlueSpec and maybe very modern System Verilog, which still doesn't quite work everywhere, and things like Chisel, is much more reasonable. And I mean that in both a cheeky sense and in a formal sense. The models that we end up extracting from these systems are ridiculously complex. If I read in a hello world program in C, and I convert it to a mathematical model behind the scenes with which we're going to reason, it often turns into tens to hundreds of pages of mathematics. But all that's hidden from you. All you see is a little squiggly line on the screen. And simple specification languages, the kinds of things that you might see, say, in old school formal tools to reason about hardware systems, you end up writing down only a few pages of logic. But as soon as you start digging in the world of temporal properties or model-based specs, which is where people are trying to drive things more and more in the world of hardware, those high-level specs get basically desugared down into hundreds of pages of logic. Now, my point here is not that these big models are scary. My point here is that modern tools capable of reasoning about this mathematics have gotten enormously powerful over the last several years. And it's a combination of the wonderful world of Moore's Law coupled with really smart, intelligent work on automated solvers, among other things. So real-world specifications, including those that we've now experimented with in the hardware world, often turn small IP blocks, say in BlueSpec, into 1,000 pages of logic, let's say. And the tools eat it for breakfast. It's okay that you end up having models that are that complex behind the scenes because you've designed your IP in a reasonable way in the first place. Now, there's been about 10 years of case studies in this topic, as Dan already mentioned over the years, that have touched on all kinds of funny areas, ranging from literally formally verified video games, which is why I was the guy that cheered about Commodore 64 in the keynote this morning, because we literally have students run Commodore 64 emulators and replicate games on, that originally ran on a 1.16 megahertz processor and a gigahertz processor, and the students can't do it, to distributed systems, to voting systems, to hardware CAD, and nowadays, in our realm, in embedded systems. For example, in a previous RISC-V event, we described a formally verified secure boot for RISC-V, wherein we did formal reasoning about the hardware, the firmware, and the software. And now we're moving into the world of reasoning about CPUs, as, for example, Clifford discussed it yesterday in his tutorial. Now, in the world of the current project, Secret Ninja formal methods have now been integrated into our world of playing with RISC-V. And this is something that our clients like, because now they get stronger assurance about the security of the platforms they might want to deploy. And when I say our clients, I mean both the federal government, DoD, IC, and the like, but also commercial firms that we work with. For example, working on formally verified secure boot for more than just one kind of RISC-V is a thing, and we hope to be making that available in the coming months. Working on rigorously validating and formally verifying many CPUs at the same time, sort of taking the ideas that you witness inside of companies with commercial proprietary tools at great effort and exploding that to a broader domain is a thing that's going on. And then there's the Best-Bin tool suite itself, which facilitates the combination of formal reasoning about security properties and evaluations against your needs with regards to power, performance, and area. The diagrams on the left show a block diagram of the formally verified secure boot on the embedded RV32 that we worked on with BlueSpec. And on the bottom left is a feature model describing that particular CPU that's been configured for the specific configuration that we verified. So here's my call to arms for you. If you want to be a ninja, let's be a ninja. So the key thing here to adopt, to talk to us about, for us to introduce you to, is to think before you do. Understand what you want to create, and actually write down a description of what you're going to build before you build it. And I don't mean a Word document. I don't mean Excel. I mean a precise description of the particular subsystem that you mean to build, or the overall SOC. And use tooling that generates evidence automatically as you work about the nature of the thing that you're building. Now for us, these descriptions of these hardware that we're writing down these days, at least in our very applied way at Galois, look like test benches, but they're not. They're actually verification benches. And they're built wholly into our design process and our methodology, such that continuously we can not only be simulating many different variants of our chips spread across many different simulators and FPGAs, but also asynchronously running formal verification tools, commercial as well as our own. The key way to get into this area is figure out in your particular group or company a small-ish case study wherein you can try to tackle things in a new way, to witness that the upside does not necessitate a PhD. It does not necessitate a trivial example. If you tackle things in a principled way, particularly if you can leverage free and open source tools rather than an experimental license at $200K a year for Jasper Gold, then you can witness success in the small and grow it to the large. So what I encourage you to do is play with the open tools that exist today. In the world of hardware, that means tools like ABC and Yosis. In the world of software, there's a plethora of tools available. Pick your favorite programming language, come up to Dan and myself during the summit and say, I challenge you to tell me the 2 greatest tools that I can use for 1 week to play with to better understand its potential positive impact on how I design and verify systems. The reason I think this is terribly important is not only because you need formal methods to tackle security challenges, but in our experience, over and over again, we're able to develop product for our customers with less time and energy than we had done in the past, or our colleagues had done in the past, just diving in and hacking, or just doing agile programming. In general, we get a higher quality outcome with greater degrees of assurance for equal or less cost and effort. Thanks.